What's up, guys? Back again with another video here. We're going to be talking more about home energy basics. We're going to talk about some home wiring in this unit. We're going to wrap up the year with this unit. We're going to go over the basics, understanding your energy bill, how you can save on energy, and how a lot of these things are measured, and some math that goes along with it. Okay, here we have the very famous band. Many of you probably already know. This is AC/DC in their prime. If you guys would all please grow your hair out, that would be just fine. I'm in the process trying to catch up to these dudes. So AC/DC, they got songs like Thunderstruck, talking about alternating current, direct current. We're going to go over that stuff today. Make sure you guys understand it. Bingo. Okay, so to understand electricity, first you got to understand what a circuit is. A circuit is basically a bunch of conductive material, typically wire, right, metals. It is the passing of electrons throughout a conductive material. So like, let's say we have a battery right here. And we got the positive side and we got the negative side. So typically, there are certain materials like that that don't conduct electricity well, and there are certain materials that do, and then there are certain materials that are in the middle that kind of conduct electricity okay. Okay, most metals do conduct electricity very well, and electricity is the passing of electrons, which are the subatomic particles inside an atom. If you remember from chemistry, okay, those are the things orbiting around, right? It's kind of the passage of valence electrons. So what happens is with conventional current, we teach that it comes out the positive end. Let's say we have a battery or a power source. If you were in a home, the positive, we call this side the hot wire, and the negative, we call this kind of the neutral. The neutral wire, which really has a way to get back to ground, but there's actually two. There's also a backup ground wire in case the neutral fails. We're going to go over that too. But basically, and so you're going to come through here. You would go out to some power source. Usually, we would see some sort of resistor that those are the things that look like a peanut, like this, right? And then they have those two legs, the wire sticking out of either end. And you're going to go to something like a light bulb, and then return home. Okay, and maybe you have, actually, let's do a little switch. Okay, and return back. If there is no connection to ground, if there is no connection to neutral, nothing in this circuit is going to happen. This light bulb will not be illuminated. Okay, if this connection is made, for example, if this swings down and connects here, the light bulb will be illuminated because there is a complete path around which the electrons can flow. Okay, so every circuit we talk about, or at least every circuit we'll talk about in this class, we talk about resistance. What resistance is, so the perfect example for me is like a river with a dam, or really just a river. In a river, there are things that get in the way of the flow of water, okay? And when something gets in the way of the flow of water, what you're doing is you are slowing down the rate at which the water can flow, or you're controlling it. And so the more resistance you have, the slower the water goes. So resistance in a river is things that are opposing the current, like a dam or rocks. And in a circuit, things that create resistance or are basically anything that's in the circuit that's going to be kind of using the electricity is going to create a little bit of resistance. The wire itself creates a little bit of resistance, just like the riverbed, something that opposes the flow of electrons. And then there are also things called resistors. And resistors are made up of the semiconductive material, and they only allow electrons to flow basically at a certain rate. So resistance is what we kind of put in the circuit to control the rate at which electrons flow. Because, for example, if if you take a little LED and you plug it into a 1.5 volt battery, you're going to get the LED is going to light up a little bit. Okay, it may not be super bright, but it's going to light up a little bit. And if you were to take an LED and you were to plug it into your wall outlet, please do not do that, but it is going to fry very, very fast because your wall outlet has 120 volts kind of powering what's going on there. And I'll move this so you guys can see that a little bit better. There we go. Yeah, it's better the way it was. Okay, so with that being said, so yeah, it's something that is opposing the current. So we, and when we're, you know, when we're building a circuit or we're dealing with circuitry, we can control the resistance so that we can control the flow of electrons. So the things that we put in to control the speed, that's kind of resistance, objects that we have control over. There's also this thing called the voltage in the circuit. Voltage is basically the amount of force that is backing the circuit. So in terms of this river, it would be like the headwaters. What is pushing the water, right? If I make a little puddle and I like on the ground in the dirt and then I carve a tiny little hole for it to go, you have this really small amount of water that's pushing the water down the river. However, if you have a great massive body of water, you're going to have more force to push water through. So you have how do we describe a circuit? Well, we can describe its resistance. We can describe the things that are getting in the way of the electron flow. We can describe the voltage. We can describe what's pushing electrons through. And we can also describe, so it's measured in volts. We can also describe the current, which is indicated by the letter I. For resistance, this is the Greek letter omega. We use that. Those are the units, ohms. There are also other units, but they're all based around ohms, basically. And then the R measures our resistance. So V for voltage in volts. That's the force. R for resistance in ohms. And current is measured in amps or amperes. It's represented by the letter I, and that I stands for electrical intensity. Okay, and what the intensity is the speed of the electrons, or rather the amount of electrons flowing through a fixed point per second. So it's like basically how fast are electrons coming through. It's not voltage that necessarily kills you, it's the current. Okay, you can have a high voltage system, but if it's not flowing into you very fast, then it's not super dangerous. It's when there are a ton of electrons are coming through your body and trying to get to ground. That's when you have a problem. Okay, so current is basically how fast things are flowing. So you guys can get a rough idea of how electrons flow here. Some sizes. So like your TV remote is 10 milliamps, and we'll go over what that is in just a second, but it's basically 100 times smaller than 1 amp. A keyboard and mouse is around 50. 1 amp is like a high-powered flashlight. Your laptop typically takes around 3 amps of electricity. A microwave would take 15. So that's the amount of electrons that are coming into the microwave or coming into your laptop per second. Okay, so what do we do? What's the math that you might do if you're on the job? Okay, that would be Ohm's Law. It only applies to systems that are purely resistive, but basically voltage is equal to the current times the resistance. And we can use this to make all sorts of calculations. Excuse me. Let's go ahead and get started. Before we use this, what you need to remember in order to use Ohm's Law is you have to have voltage in volts, current has to be in amps, and resistance has to be in ohms. And so oftentimes you're presented things like milliamps and milliamps or kiloamps or something like that. So basically, you need to know your metric prefixes here. So 1 amp is 1,000 milliamps. A milliamp is smaller, so it is smaller than an amp, so there are more of them to equal 1 amp. Just like 1 foot is bigger than 1 inch, and we have 12 inches, we have more of them that make up a foot. Okay, so 1 amp is 1,000 milliamps, and it is 0.001 kiloamp, which is tenths, hundredths, thousandths, right? So, so 1 amp is 1,000 times stronger than a milliamp, and 1 kiloamp is 1,000 times stronger than 1 amp. So that means that you really just move the decimal place over 3 places. So when you're going when you're converting from kiloamps to amps, you times by 1,000 because you need 1,000 more. Okay, so this direction is timesing by 1,000 when you're going to the smaller unit because there are more of them, and when you go this direction, you take the number and you divide by 1,000. So 1,000 divided by 1,000 is equal to 1. 1 divided by 1,000 is 0.001. So that's how you are getting from step to step in these conversions. So if we have 4 kiloamps, what is that in amps? I'm going to move these out of the way a little bit. 4 kiloamps, what is that in amps? Well, 4 kiloamps is, we're starting in kiloamps, we're going to the smaller unit, which means we need times by 1,000. That means that's going to be 4 times 1,000, or 4,000 amps. Okay, and so that's equal to 4,000 amps times by 1,000 again, which is 4 million, 1,000, 10,000, 100,000, million. Okay, 4 million milliamps. Oops, just do MA. Perfect. So if this is in amps, that's red. The prefixes work the exact same with volts and with ohms. So if we have 8,756 millivolts, we have the small unit, so to get to the bigger unit, we have to divide by 1,000. So take this, divide by 1,000, or it's the same as moving the decimal place over 3 places. You get 8.756 volts. So it is 8.756 volts. Divide by 1,000 again, or move the decimal place over 3 more places. That is 0.128756 kilovolts. So kilo is the prefix, meaning 1,000, and milli is the prefix, meaning 1/1000th. In green, if we have 330 ohms, going to kilo ohms, the symbol is like this. For how many is kilo ohms? This divided by 1,000, 0.330, and here times by 1,000 is 330,000 milliamps. Why am I teaching you this? Is because we are, protecting circuits and practicing doing calculations with these and being able to understand how much of one thing is in a circuit or not. So we're going to move on. If a circuit with 120 volt power supply is drawing 5 amps across a device, how much resistance is that device providing? Well, we can use Ohm's Law. Ohm says that the voltage is equal to the current times the resistance. Let's set it up. We say V equals I times R, like so. All right, so 120 volt power, drawing 0.5 amps. So this is in volts, this is in amps, so we're in great shape. So we can set this up as 120 is equal to 0.5 times the resistance, like so. And to solve, we divide both sides by 0.5. I'll do that in a different color. Divide by 0.5. And we end up with, keep the same, resistance is equal to 120 divided by 0.5, which is 240. So the resistance is equal to 240 ohms. Okay, if a circuit has 120 volt power and is drawing 5 amps, there is 240 ohms of resistance. So this resistor is setting how much amperage is being sent. Find the voltage across the circuit with 330 ohms and 20 milliamps of current. Okay, so this is V equals IR. Which ones do we know? 330 ohms, we know resistance, and 20 milliamps of current. That's this. So we know I and R here, okay? So we don't know voltage, so we're going to say V equals, I can't plug in 20. I saw you almost try and do that. Be careful. 20 milliamps cannot go in here because it's in milliamps. We have to convert. So 20 milliamps, okay, when you're going from a smaller unit to a bigger unit, you divide. 20 divided by 1,000, 1, 2, 3, is equal to 0. I'll draw a little line here. 0.02 amps. 0.02 amps is 20 milliamps. So we're going to plug in 0.02. That's the number we have to use. We cannot use 20. Times the resistance, which is 330 ohms. So 0.02 times 330. 6.6. So this circuit is being powered by 6.6 volts. So make sure when you are doing these calculations, make sure you convert to the base unit before you plug in, and make sure you write your units on your answer. Okay, a standard 5mm LED can be ruined if they experience a current higher than 20 milliamps. If I hook up a 9-volt battery to a circuit with a 150 ohm resistor, is the LED likely to be ruined? Okay, so I have a lot of information here. So they're going to be ruined if they experience higher than 20 milliamps. A 9-volt battery is our power supply. Start with Ohm's Law. 9-volt battery is our power supply. We have a 150 ohm resistor. So basically what we're saying is we know this one and this one. This is what we have, and we're going to use it to make a judgment call with this. So we have a 150 ohm resistor, we have a 9-volt battery. So if it's a 9-volt battery, equals the current, which we don't currently know. We're checking the current against this, okay? Current times the resistance, which is 150 ohms. We do 9 divided by 150, which is 0.06. I equals 0.06 amps. Okay, well, this is milliamps. In order to convert them, I'm going to turn this into milliamps. 0.06 milliamps times by 1,000, 1, 2, 3. That's 60 milliamps. So if we have a 9-volt battery and a 150 ohm resistor going to an LED, then that LED is receiving 60 milliamps of electricity, which exceeds 20. So since 60 is greater than 20 milliamps, the LED will burn up. Okay, that's the basics of Ohm's Law. So you're gonna have some problems to practice there. Basic one-step equations. I believe in you. Okay, make sure you convert your units before you plug them into the equation. I want to go over a couple other things really fast, kind of the history of what the history of some electrical theory, basically. Okay, so direct current is what we're kind of doing math for now. It's just like when you have, or like your basic circuit that we're all familiar with, like you have a battery, the electrons are flowing out the positive end into the negative end, or at least that's what conventional current is. Okay, out the positive into the negative, that is direct current. So electricity flows one direction from high voltage to low voltage. The person that formalized this was kind of Thomas Edison. In most parts of cars, most electronic devices, solar panels, so on and so forth. So solar panels are taking energy from the sun, sending them electrons down the wires to be stored in batteries or charged batteries to be used for later. Okay, so yeah, direct current is usually how these things operate. The advantages of direct current are that it's super, super simple and it's super portable. So you usually have some sort of battery or some sort of charging device you can bring along with you. Easy peasy. The disadvantages: it's difficult to convert it to AC. So it's hard to take, and I haven't told you what AC is yet, but it's alternating current, right? Direct current, it's very hard to change into AC, and I'm going to show you how that's changed. And it's also very difficult to change the voltage with direct current. If we can't change the voltage, then that makes it very, very hard for us to have a 120 volt circuit and plug something like a phone in with direct current. That'd be pretty tough. Okay, so disadvantages: difficult to convert to AC. I'm going to talk about how that's done in just a second. And it's difficult to change the voltage. Advantages is that it's simple and it's portable. The person that really helped us the most with alternating current was a man by the name of Nikola Tesla. He worked for Thomas Edison and ended up kind of going off on his own thing. But electricity flows back and forth in a circuit, and this is usually created by a large magnet. So what happens is, you know that opposites attract. So what happens in alternating current is, if this is your wire, imagine it like a tube, and electrons are flowing, they'll kind of want to flow one direction. If you have a magnet right here with a negative charge and a positive charge, and that magnet is spinning, like so, if it's spinning, okay, opposites repel. So the electrons in the wire are going to want to go this way when the magnet is facing in this direction. And when the magnet is turning, it hits this phase here, when you have your negative and your positive, like that, okay, and the wire is like this, the electrons don't move at all. They're stopped, okay? And then when, let's keep going, make this a little bit bigger, okay? And then as the battery continues, as the magnet continues to spin, you get this, you get the positive here and the negative here, and the positive opposites attract is pulling electrons back this direction. So you get this motion back and forth in the wire, and this is what you have to do. You have to have a big magnet pulling on the conductor. So basically, we're going to go over the advantage and disadvantage for just a second, but this is why it's so difficult to convert, is you have to have like kind of a magnet to do it. And yes, there is a magnet at our power plant that is doing that is shifting the electricity back and forth, shifting the electrons back and forth inside the wires in our walls. And in fact, it is shifting back and forth 60 times per second. There are 60 cycles per second, so it goes. So that means the lights are turning off. I guess that's a half cycle. So that would be at 60 hertz. I guess they would be turning off 120 times per second, okay, because they turn off here and here and then here and then here. So 120 times per second, our lights are flashing. This is why, certain times if you take like a high-speed video of the lights, like if you take a slow-mo, our eyes cannot detect that the lights are flashing, but the lights on the power grid everywhere operate at 60 hertz, and or at least for the most part. I don't know of an exception to that. And our eyes cannot detect them flashing, but things like high-speed cameras and stuff can see the lights flashing. And if you slow that down, if you take a slow-mo video, you can, it happens. You can look and you'll notice a difference. So electricity is flowing back and forth. It's in large power grids and homes. The entire cycle 60 times per second. So it turns off 120 times. Okay, advantages. it's super easy to transform the voltage. So you can take AC, and I'm not familiar with how that process works, but you can take 120 volt power and you can very quickly dumb it down into something just like with a converter like this one that I'm using for my monitor. You can take 120 volt power. This is an AC adapter, and the output is 20 volts. It says right on. So input is 100 to 240. The output is 20 volts. And so it says the conversion that the adapter is doing. Super easy to do. That's the advantage of AC. Okay, it's also really, really easy to convert to DC. That's another reason these adapters are important. So it says the output is 20 volts. Oh, it doesn't say DC, but it should be DC. Okay, because we don't want our computer turning on and off, right? We want direct power happening, direct current going directly to our computer. Disadvantages. It's not as portable. Like our laptops are on DC. We can just get the battery, take it with us. AC, you need that big magnet, which is a problem, okay? Unless you're, so, portable AC is tough, okay? It doesn't work with many circuits naturally. So like a laptop, or is the example I gave before, you don't want that turning on and off. Lights are an exception because our eyes can't detect the flashing that we experience in our house. Okay, cool. That's the difference between alternating and direct current. Did you know that if you travel to another country, the plug from our country is probably not going to fit? So if you want to go on an international trip, you typically have to buy a converter or an adapter for their walls. Now you're probably asking yourself, how is it different? Well, some of them are different, some of them are not. Okay, Japan's is, it only has 2 prongs. Ours have 3, and we're going to go over the history of the receptacle in here in just a minute. Japan's has 2 prongs, ours have 3, but our plugs will actually kind of, as long as we don't have a ground, some plugs that we have, that's this port, some plugs that we have will fit in a Japanese socket. So the countries that have the same plugs we do, Canada, Mexico, and Japan. If you travel to any of these other countries, the UK, Germany, anywhere, this is the European Union flag. If you go to somewhere else, basically they're not going to have these ports, or they're not going to have the same ports we do, and you're going to have to buy a device that's going to convert that. Also, other countries run at different voltages. So the reason you have to have a converter is if you could plug if they did have the same plug as us and you plugged into their power, they actually have like 220 volt or something in the wall sockets. So that you would cook your phone. You'd be sending way too high of a current. The resistance in your phone is set up for 120 volts. So if you plugged it into the wrong socket, you would cook your phone and ruin it immediately. So if you travel to another country, you got to make sure you have the correct converter before you leave. Okay, the standard home receptacle is 120 volts. We've gone over that. They look like this, and they have the following ports. The big one is the neutral. The small one is the hot, and this one is the ground, and that was added later. If you have any really old appliances or like grandpa's old lamp or something, it probably doesn't have this port. And some plugs that we have don't have this port. Anything that's got, like, usually anything that has metal on it, any device that has metal is going to have this ground port, or you're going to have a prong that is going to send excess electricity elsewhere and not through you. And we're going to go over how that works. So the green screw is connected. So if you look at a standard sheet of wire or sheathing wire that you can buy, this is like 12-2 wire that you buy at Home Depot. It comes in a yellow sheet. It's 12 gauge wire. That's where that number comes from. The black or the hot would be connected to your brass. So the rule is white goes to bright, black to brass is the rule for connecting a receptacle or a light. You're going to see these different colored screws. The bare wire is the ground wire, and that is what is hooked to your receptacle. So if you live in an old house, there's no, they may have these colors in your walls, but they may not have been hooked up correctly. So there's no guarantee that how you have an old house wired is correct. There was a lot of stuff that was wired incorrectly in our house. But basically, black to brass, white to bright, and then the bare one or the green wire is connected to ground when you are wiring a home. Okay, I want to pull up a video here, and you can watch this on YouTube. You should go check out this guy's channel. I'm just going to stream it on here so I can have some commentary for you. We're going to watch it together. So I hope you enjoy it. This is the history of our electrical receptacle.
Hi folks, here in North America we have this funny looking receptacle which kind of looks like a surprised face with one eye bigger than the other and a big open mouth. Other countries have similar odd-shaped receptacles for similar reasons. I'm going to give you a bit of a history lesson to explain how it came about and why it is like it is. In our electrical system, for electricity to flow, we really need only two wires. The actual electrons in the wires don't go very far, they just move back and forth, what we call AC, or alternating current. And originally that's all we had. The receptacle had just two identical holes in it. The problem is that by interacting with the surrounding air, the long wires leading back to the generating plant would build up a different form of electricity called static electricity. This is just a buildup of electrons that aren't going anywhere. The problem was that this buildup of electrons got so great that eventually it all of a sudden burst out of receptacles and shocked people. Another problem occurred when lightning struck the wires. This would cause a sudden surge of electrons flowing through the wires, which could cause damage to appliances that were plugged in, or even jump out of wires behind walls to shock people nearby.
So the electrical code is changing in homes quite drastically, or it has recently. Like I did some wiring in my house and looked at an older book for reference, and what some of the wiring that I did was incorrect because it was correct in the book, but the code has changed. So you got to keep up on it. And we kind of have adapted. We realized what we've done in the past wasn't safe and have adapted it since then.
All solved by connecting one of the two wires to the earth, or ground as we call it. Electrons no longer built up on the wires but went to ground instead, and that electrical current from lightning strikes also went safely to ground. But now there was a new problem. Our bodies can conduct
electricity. All right, so the first thing was we had the static electricity, we had lightning strikes. If that hit the wires, it was coming out in our home. So we installed ground wires outside, and what the ground wires would do is take that static electricity and the lightning and send it into the ground instead of into us.
If we're in contact with the ground and we're not wearing shoes that don't conduct electricity, like ones with thick rubber soles, then we're a conductor to ground. If we touch the wire that's connected to ground, then there's no problem. But if we touch the other wire, then the electricity will conduct through us to ground. We get shocked.
So if we're not wearing insulated shoes, it'll come through us and try and find a path to ground.
The solution? Everyone was taught not to do that. To further emphasize the danger, the grounded wire became known as the neutral wire.
That was their safety precaution. Their safety precaution was, hey guys, don't touch the hot one. Whoops. Yeah.
The ungrounded wire became named hot. Different colors were used for the insulation on the two wires. In North America, the neutral one was colored white, and extra insulation was added to the wires, especially the hot one. But there was still another problem. Some manufacturers were connecting one of the wires to the metal cases of appliances. If that was the hot wire, and a person who was in contact with the ground touched the case, they got shocked. Rather than make manufacturers change the way their products work, they were told to use the neutral wire when connecting to the cases. Since the neutral wire is connected to ground, there was no problem. Also, the plugs were changed. The neutral prong was made wider than the hot prong. And of course, that means the receptacles changed to have one hole taller than the other hole. That also meant the electricians now had to connect the neutral wire to the taller hole and the hot wire to the shorter hole. But that still left a problem. What if the hot wire inside the case becomes damaged and touches the case? Since the case is connected to the neutral wire, the electrical current should go to ground, possibly tripping a breaker on the way. But what if the metal case isn't connected to the neutral wire? Or if the electrician wired the receptacle holes backward? When someone touched the case, they got shocked. The solution? A third wire was added, whose only purpose was to be connected to earth ground. Manufacturers were told to always connect metal cases to this wire.
It is code that everybody has paths to ground within their homes, so that excess electrons can have a place to go that's not to you. Electrons are going to take the path of least resistance, and you just don't want that to be your body.
In North America, the insulation for this wire was colored green to be a different color than the other wires. Of course, that meant we now needed a third prong in the plug and a third hole in the receptacle. The new prong...
So why do some of our plugs still work if we don't have this? Because these are the parts. So basically, if I could boil it down, these are the only two you need for a circuit. Okay, you have your incoming and you have your outgoing, and then so your incoming and your outgoing. But what this is a safety precaution. It's basically a second way for things to go to ground. So this is one way to go to ground, the neutral, but this is a second, or rather a backup way for that to happen.
To look very different than the other prongs, and so was the hole. That way there'd be no chance of connecting anything incorrectly. And that's the story of how we got our surprise faced receptacle. Well, thanks for watching. Be sure and check out my YouTube channel, rimstar.org, for more.
Yeah, got a cool channel. Loved it. Great job. It was a lot of fun. Hope you guys enjoyed the video. Check out that guy's channel. It rocks. Also, you have an Ohms Law worksheet to do. Thanks for tuning in. Let's be careful out there. You got this. See ya.